Hi, and welcome to this brief discussion basically of some of the problems from chapter 43. The problems I have in mind are actually problems 44, problems 46. Problem 46 and 47 are similar, except one of them deals with the proton, the other one deals with the neutron. And problem 51 and problem 70. Okay, which is really a data problem. Okay, so let's discuss quickly what these problems are and see how we're going to solve them. Problem 44 says the nucleus of beryllium 410 isotope, so basically Be 410, 6 neutrons and 4 protons, undergoes a beta minus decay. The atomic mass of beryllium is 10.01355 U. How much energy in MeV is released in this decay? So basically we have to first of all determine what happened in here. So this element in here will go a beta minus decay. In the beta minus decay, one of the protons in here changes into a neutron. So the element in here that we're going to end up with hold on, that's not correct. Okay, so this number will rise to 5 actually. So the element in here is 510, and if I look at this plus usually a neutrino in here. Okay, so let me look at the element in the periodic table. Looking at the table that I mentioned in the lecture, table 43.2 is a very important table for all of these homework problems basically. We find it because we need to find what the element is in here. So why am I having that page? 14. Okay, 1445 the pages. So yes, it's the boron, and so we need these numbers in here. So beryllium, they tell you it's 10.013535 U, and boron from that table is actually equal to 10.0 12,937. I mean, in terms of mass, this mass is higher than the other mass, so definitely this reaction is possible, and we should really account for the fact that this is a so one of the neutrons in here went through a beta minus decay and converted itself to a proton. So that's exactly what happened in this nuclear reaction. So how much energy in MeV is released in this decay? Well, in this case, I'm going to add this mass to that of the electron. This is negligible mass, actually practically is 0. It's 10 to the negative 36. It's less than 10 to the negative 36 kilograms. One of the research that physicists are doing nowadays is trying to determine the mass of the neutrino. We know it has a finite mass. At least some of the neutrinos do. Not all of them do. There are 3 types of neutrinos, actually 3 pairs of neutrinos. Okay, there is the muon type, the tau type, and the electron type, and with their antiparticles. Anyway, so we're going to add the mass of the mass of the electron, because that's what the beta minus is, to that of the to that of the but this is also included in it. This number is already included in it, so it's just the difference of the two masses, because this number is already included. The mass of the boron itself has the electron included in it, so it's just the difference in the two masses times the speed of light, or just multiplied. So it's this number minus this number, and that's going to be just basically delta M is going to be this 10.013535 minus 10.001297, and the whole thing is multiplied by c squared, or 931.5 MeV. Okay, so that should give me an answer for the energy. So that's the first part. The second part, it says in here, if you assume that all of the energy released in the decay appears as kinetic energy of the beta minus particle, a very accurate assumption, what is the speed of the beta minus? Okay, we're going to convert this. So basically what we're saying in here is that all of this energy is that of the electron, and the energy of the electron then is going to be just basically gamma mc squared, where this is this energy, and gamma minus actually mc squared for the electron, so it's going to be mc squared times gamma minus 1, and we already computed this energy from that expression, okay, which is delta m times c squared from this expression. So we have that number. From here we're going to find the value for gamma, which is just a solution to this equation, which is delta m over m plus 1, and that should give me a gamma value for gamma. And from here we're going to solve for the velocity basically through this expression, because we're not guaranteed that the relativity is not I mean, don't try this expression because you're going to get it wrong. 1/2 of mv squared, that's not going to work, this classical expression. As a matter of fact, gamma will be probably 2 or 3, it's unitless anyway. You find the value of beta, and beta will be almost that of the speed of light, about 90% the speed of light. Okay, so relativity cannot be neglected for this problem. So this is basically, I'm not doing them in detail because I'm hoping that you guys go through them and do them and check your numbers, check your work and all of that. Okay, so this is problem 44. Problem 46 and problem 47 are identical. Okay, problem 46 says calculate the minimum energy required to move one proton from carbon 12. This is called the proton removal energy. Hint, find the difference between the mass of carbon 12 of a carbon 12 nucleus and the mass of a proton plus the mass of the nucleus formed when a proton is removed from carbon 12. Okay, we're going to go from 6 to 5. Okay, and where is the mouse? We're going to go from 6 to 5, and again we're going to go from the new element will have 5, the number z5, and then also in this case 11. So that must be, again, it's a boron, okay, plus again the proton in this case. So that is basically the reaction that we're supposed to have in here. So what we're saying in here is add this mass, and again you go back into the same table on page 1445. That's table 43.2. Here's the table. This mass is exactly 12. This mass is, it's an isotope of the boron, 11. So it's 11.009305. Okay, and you add to it the mass of the proton, and you find the difference between them, and you multiply that by c squared, and that will be the energy required to remove a proton. Okay. How does the proton removal energy for carbon 12 compare to the binding energy for nucleon for the, so basically we have to again calculate the binding energy for this E over 12, because A is equal to 12 for the case of this carbon. Okay, the binding energy, and again what we're supposed to do is Z is actually 6 times the mass of the hydrogen plus 6 times the mass of the neutron minus the mass of the carbon, which is 12 in this case, which is exactly 12, times again 931.5. Okay, MeV. Okay, and this is 1. I'm using in the dimensionless units already, so don't plug in U in here. I already converted that into MeV. So again, it is what, 1.00 some 78 or something like that. This is 1.0086 something like that, 665, and this is 12. So this is times 6 times 6, and you subtract the 2, and that is going to give you the energy in this case per nucleon for the case of the carbon-12, similar to what we did in lecture for the deuterium in this case. Now at the end, you're going to find two values, this difference in energy versus this difference in energy, and you will find that this is actually going to be roughly about half of that much. Okay, so it takes a lot of energy to remove a proton from carbon. Problem 47, it's a similar idea, except now first of all we don't have carbon, we have oxygen, the isotope 17 of oxygen, and it's called and then we're going to remove a neutron from this one. So when we remove a neutron, the number Z does not change, so we're going to end up with the same thing, oxygen, except now we have 16, the mass number in here will drop to 16, plus of course one neutron. And again, we're going to find the mass of the oxygen. We go back into the same table to find this mass, and to find this mass, and to find this mass, and find the difference between the both of them, and that's going to be just basically the difference in energy. Now, how does the neutron again compare to oxygen? So what we're going to do in this case, we're going to use the same formula as in there for this case in here. So we're going to find the binding energy for this isotope of oxygen, which is going to be 8 masses of the hydrogen plus 9 masses of the neutron, minus, again we're going to have to look at the periodic table to see exactly how much this number is. Not periodic table, I'm saying the same table, 43.2. Oxygen 17 is 16.99132. times 931.5 MeV. Okay. Again, we're going to find the number in here. We're going to do this. We're going to compare this to, and here we're going to find that it's actually a little bit easier to remove that neutron, and since the energy will be less than the binding energy per nucleon. Okay. So this is problems 46 and 47. Let's look at problem 51. I was tempted to do problem 57, but again it's a little bit long. So again, the atomic mass for problem 51, the atomic mass of manganese 25 is 24.985837 U, and the atomic mass of aluminum 25 is 24.990428. Which of this nuclei will decay into the other? Compare the masses. Which one has more mass? Obviously it's aluminum 25 has 24.99, whereas the magnesium in this case has 24.98. So it's the aluminum that is going to convert into magnesium with a beta decay in this case, because the Z number has changed. Okay, it's actually beta plus decay because the number has dropped from 13 to 12. Okay, so that's one way. Or you could do an electron capture also. That should do the same thing. Okay, that should do the same thing in terms of the both reactions are possible. What type of decay will occur? So it's going to be either a beta plus or an electron capture. Explain how you determine this. Again, we just find the difference in the masses, how much energy in MeV is released in the decay. You have the two numbers. The first one you're going to just subtract the 2, and that's going to give you the energy. In the second case, you're going to actually add the mass of the electron to the manganese and subtract it from that of the subtract the total from the mass of the aluminum, and that's going to be the difference in the energy again. Okay, don't forget to multiply by 931. Okay, problem 70. So I already discussed problem 51 without writing anything on the board. I'm sorry about that. Hopefully you guys can. Okay, let's talk about problem 57. I know I did not mention that, but it's important because that deals with the. It's still radioactivity in this case. Okay, radioactivity. Okay, so it says in here you have technetium, which is an element whose atomic number, mass number is 99. Were discovered in red giant star. Red giants are very old stars, often around 10 billion years old. Okay, if you look at the HR diagram, stars, most of them they fit, or they. So this is the color of the star, and this is basically the luminosity of the star. So if you look at them, most of the stars they live in what is known as the main sequence stars, like the sun is somewhere in the middle in here. And then in the HR diagram, so this is called an HR diagram. You have a region in here of red giants, stars that have already basically exhausted their core hydrogen, and now they are actually going through the red giant stage. So now they are in the final basically stages of their life. And then there are super giants also in here, and this one will actually migrate and end up in this case in here in the so-called white dwarf region. Okay, if you took astronomy, you understand exactly what this means. The bottom line is in here it's at the end of its life. The point is, when stars are in the main sequence stage, most of the time they produce as much as up to iron. Okay, in this case in here, unless they go through, and this is through nuclear. I know I did not really talk a lot about this one, but hopefully you guys can go through. We have some problems actually. Problem 52 talks about that one, the fusion and the reaction in the sun. So hopefully you guys can look at these problems, problem 52. But let me finish this point in here for problem 57, and then we'll probably go to talk briefly about problem 52 still. So the point being in here is that this element could have been created during this, when the star was its main sequence star. The point is, it's not going to turn out to be correct because of the fact that technetium is of a different. It must have happened. It must have been created at the end, toward the star, when the star actually went through toward the end of its life cycle, through some sort of violent events. Okay, so red giants are very old stars, often around 10 billion years, so near the end of their life. So technetium has a half-life of 200,000 years. So that is its half-life. Remember, the star has an age of about 10 billion years, or 10 to the power 10 years. That's more like it. Okay. For how many half-lives has the technetium been in the red giant star if its age is 10 billion years? Well, if it's really 10 billion years, then in this case it would have gone through this many lifetimes, 10 to the power 10 divided by 2 times 10 to the power 5. And this will be 10 to the power 5 and 10 to the power 5, so we'll be left with 10 to the power 5 divided by 2, and that should be 5 times 10 to the power 4 half-lives, basically half-life times. That's a lot of times, okay? 50,000 times. So the question is, what fraction of the original technetium would have been left at the end of that time? Well, if you calculate this number, this is not just half. So let's say, for example, let's work out the problem backward. Okay, let's say, for example, we have just one atom left, and that's the one that we were lucky enough to actually detect in our spectroscopic analysis of the star. Okay, then in this case we must have had a number that we started to decay, again exponential of minus t over lambda, from this number n naught that we need to find. And at some point we're going to find the 1 in here, and we're given lambda. So lambda in this case, since we have the half-life, we're going to compute it in there. We have t, we have lambda, or lambda is related to that number. So we're going to find the number in here, and the number will turn out to be a huge number. Okay, the number is going to be a huge number. As a matter of fact, is going to be of the order of 10 to the power 15,000. Okay, and how much mass that is? Well, the mass number for this technetium is 99 times the mass of 1 U, which is 10 to the power negative 27 times 1 for all practical purposes, if you like. We're doing just an order of magnitude, times 10 to the power 15,000. Okay, that is how many of them were initially. Okay, so if you do the math in here, 15,000 minus 27 is negligible, so it's roughly 10 to the power 15, because 15,000 minus 15 minus 27 is practically 15,000. So that is how many kilograms? 10 to the power 15,000, not 15. And that is too massive. For example, for the sun, it's 10 to the power 30. So there is no way that this could be a star. So this technetium was not created during when the star was a main sequence star. So it talks about another violent event that created these elements. Okay, so let's talk about problem 52. Problem 52 also is something that we didn't talk about. So problem 52, basically, you have a proton inside the sun and another proton inside the sun or the star. They combine, and one of the protons will convert into a neutron. So there is actually an electron positron, that is, okay, that is going to be emitted, plus a neutrino. In this case, you are created actually the isotope 2 of the hydrogen. So this is one reaction. This H12 is actually a little bit stable, and it has a very long lifetime in this case. So there is a chance for it to meet another one of the same type, and this reaction will create, no, I'm sorry, it will capture actually another proton. So another proton will come in here. So this is one scenario for this one, and now you end up with two protons and a neutron. So this is actually the isotope 3 of helium in this case, which will combine with another isotope 3 of the same helium that required actually 3 more protons. So imagine that there is actually another hydrogen, and 3 of them. This one will give you deuterium, and this one will combine in this one, so that you will end up with another, again, this isotope of helium. Now these two isotopes of helium, when they meet, they will give you another combination. It gives you a regular helium in this case, plus of course this excess of hydrogen that are going to be expelled. So 2 hydrogen protons that are going to be expelled in this case from this reaction. Now if you count the numbers in here, you started with 6 protons. The final product is a helium atom plus 2 protons. So there are actually at the end the net 4 protons combining to give you one helium atom. This process is called proton-proton process, and this is actually the main process of how neutrinos, because each one of them will produce a neutrino. So on this side we're going to get a neutrino, from this side we're going to get a neutrino. So each time we're going to make a hydrogen, basically atom. What happened to this guy in here? Of course there is gamma energy in this case. There is gamma radiation that is going to emerge from this one. It's going to meet an electron that are floating in there, and they will annihilate one another, and again you're going to get 2 gammas in here. So at the end, the main thing in here is that's going to be an energy, and gamma energy, we're going to go through Compton scattering, a lot of it, and I think we had a problem with that. We discussed it. That is going from previous chapters. That is going to go through a lot of Compton scattering, and before the time it gets to, and it takes hundreds of thousands of years before it reaches the Earth, or before it actually escapes the Sun, before it escapes actually the core, and then from the core it's going to go to the radiation zone, and from the radiation zone it's going to move a little faster in the convection zone, and finally it's going to escape the Sun. So the photons, the light that we have in here, existed for hundreds of thousands of years. However, neutrinos interact very little with any matter, and they will go straight through, and they're the ones that are going to be captured on Earth, and they're proof of this decay. There is another process actually that involves a shortened version of this one. So you have two protons, so this part of the cycle is true, but then you're going to have a helium in this case that is going to combine with them, this directly, one of them, and it's going to give you a proton plus the helium in this case, and at the end you are going to still end up with two neutrinos, and that represents about 17% in this case. So this is of type 1. There is type 2 also, a proton-proton chain, proton-proton process through which the energy of the Sun is released. Again, this is just in a nutshell, so that you have an understanding. We'll have to do problem 52 if you're going to do it. The balance of the power in here is that every time the fusion reaction, all of this one will lead you to about 26.73 MeV from this reaction. That is the net energy that you're going to get. We also know that the power that is emitted by the Sun is 3.8 times 10 to the power 26 watts. That's how much the Sun is losing energy per second. So this is a joules per second. It's worth converting this number, or at least this number, to joules, so that you have an idea on how to work with these numbers in the same units. Now estimate how many solar fusion reactions take place every second. Well, in this case you have this number. Every time there is a nuclear fusion, you're going to have that. So all you have to do is just divide this number by that one. After you do the proper conversion in here, because this number you have to multiply it by 1.6. There is 10 to the power 6 in here. 1.6 times 10 to the negative 19 times 10 to the power 6, and you divide that by that, and you're going to get a huge number for how many nuclear reactions there are going to be. They're going to be of the order of 10 to the power 38 or something like that, which is a big number. Okay, so that is the ratio with which how many basically of these things are happening in the Sun. And estimate the number of neutrinos that live. All you have to do is just multiply 10 to the power 37, I think, yeah, more appropriate. 10 to the power 38, because it's going to be 9 times 10 to the power 38. So 10 to the power 37. So this is how many nuclear reactions are happening to give you that much energy every second. Okay, and every time there is one of them, one of these nuclear reactions, you're going to get 2 neutrinos. Okay, so you're going to multiply that number by 2, and from there you're going to see. So the neutrinos, when they leave the Sun, they will go in every which direction, all the directions. This Earth is here only, and it has it's facing the Sun by this area pi r squared, where r is the radius of the Earth, and this is the distance in here is actually a sphere with which the neutrinos will spread, and that area is 4 pi the distance from the Earth to the Sun squared. Okay, so this number is 1 AU, 1 astronomical unit, or 150 million kilometers. This radius of the Earth is about 6,400 kilometers. So again, you're going to do the ratio. All of these neutrinos, they will spread every which way. You're going to find this area divided by that one, and you're going to have that how many neutrinos actually land on the Earth. And then you're going to divide that by the area on the Earth, and you're going to find exactly how many per centimeter cubed, so that if you're going to do the experiment, what to expect in here. Problem 63, I didn't mention problem 63. That's also one of the problems we're going to be talking about in here. Problem 63 actually is that that is the other type. The Sun produces a minority 17% of its helium for using the proton-proton two-type chain in which 4 protons and an ambient alpha particle produce 2 alpha particles. I'm sorry, so that's and 2 neutrinos and at least 4 protons. So we're going to use this percentage and use with this problem. So I discussed the other one extensively, so hopefully you guys can go through that. Okay, problem 70. This thing I didn't really want it to go into too long. I'm trusting that you guys will do these problems because I'm actually not doing them, I'm just discussing them. And if you have difficulty with them, please let me know. Anyway, problem 70 gives you the time. So you have a sample in here of some material, okay, an hour, and it gives you the decays per second. I know I gave the expression in terms of the number of the actual particles given by n naught exponential of minus lambda t. If you take the derivative of this expression dn over dt, it's going to simply be equal to minus, what is it, n naught over lambda times exponential of minus lambda over t. Why minus? It's minus lambda directly, I'm sorry. Okay. What I'm going to call then this one is, it's actually equal to, this is the activity, okay. So the activity by definition is going to be given by, first of all, dn by dt is going to be defined as minus the activity in this case. So we're going to have the activity is given by a naught exponential minus lambda t. So the activity or the number of the actual object in here, the element in here, are proportional to one another. Both of them are characterized by. This is the properties of the exponential. The exponential is its own derivative basically. Okay. And what they gave you in this case, they gave you the decay, they gave you the activity. They didn't give you the actual elements in here. And what you're supposed to do in this case is you're supposed to plot the natural log in here of the ratio, or ln of a, should be some constant which is ln of a naught minus lambda t. Okay, so if you plot this one in here, it should really be a line. Okay, but if you plot this data from this problem, it's not going to really fit into a line. It's going to fit into a line after 5 hours. So you will notice that the plot looks kind of weird a little bit, and then it becomes straight line. So this is not a correct. So after 5 hours, it becomes a line. So what this suggests is that you have in the sample two different materials. And as you were recording the radioactivity, in this case, after 5 hours or so, the first sample completely decayed. So it must have short-lived sample, short-lived part of the sample. And this one now is the long-lived one. So we're going to find the slope of this one. The slope is going to be exactly your lambda for it. And then you're going to subtract this activity from the other activity to find that of the short-lived and replot the other one, and it's going to also be a line for it, and you're going to find its slope and you're going to find its lag time. So this is in a nutshell basically discussion of these problems from this chapter. If you really need more details or if you have any questions, please let me know. I'm going to stop the recording right now. It's half an hour, so that's exactly what I was hoping to do. Okay, thank you.